And we are live. Oh, that's me first. Okay. That's right. Okay, so for this first question, it's asking about a virus genome, and it is asking for what if it's double or single-stranded DNA or RNA and circular versus linear. So for virus 1, I put double-stranded because all of the complementary pairs were 2% off. So I figured that was kind of close enough. It's RNA because it has uranine, and right? That's how you pronounce it? Is it uranine?
Yep. It's uranine.
Okay, just wanted to make sure. You laugh. Oh. And then since it's resistant to exonuclease but sensitive to endonuclease, it's circular because exonuclease chews at the end of the strand. And if you're a circle, obviously there's no end to eat at. So virus 2, there was more than a 2% difference in the complementary strands or complementary bases. So I said it was single-stranded. It has uranine, so it's RNA. And since it's sensitive to both exonuclease and endonuclease, it's going to be linear. Virus 3, it's double-stranded. Since it has thymine, it's DNA, and it's sensitive to both, again, so it's linear. Virus 4 is single-stranded. It of uranine, so it's DNA, and it's resistant to the one but sensitive to the other. It's going to be circular.
Okay, so I have question 2. So question 2, it's basically going through the lecture notes and the PowerPoints from this week and just plugging and chugging. That's all you really need to do. So A, we got topomerase 2 and nucleosome. B, we got 2 nanometers wide and then 0.34 nanometers in the DNA double helix. C, topomerase 1, and then D or C. And then E, we have 35S, or referred to as sulfur, and then 32P, which is phosphorus. And then F is the sugar, and uridine is ribose. And for deoxythymidine, sorry if I butchered that, deoxyribose. Okay, I also have question 3. Hopefully this is laid out in a way that is easy to understand because I just plugged and chugged. So we have 109 plus 48 million base pairs. That's what BP stands for. So we got 157 million. I put it into scientific notation just to make it look a little neat and easy to plug into my calculator. So I times that by 0.34 times 10 to the negative 9th, because that's equal to 1 base pair, and I got 5.3 times 10 to the negative 2nd in meters. Okay, and then B, I did the same thing. I took my 157 million, and 1 nucleosome is equal to the 50 plus 146.5 base pairs, and then I got 798,982 nucleosomes. And then we take this number, so hopefully we got it right, because if not, then we're going to screw up C. And so then you just times it by 2 by the 2 histones that it's asking for, which then gives us 1.6 times 10 to the 6th nucleosomes. All right, and then D, this one, you had to do 2 separate ones because it's asking for it. So we have the first one, which is 157 million again, and you times that, you divide that by 25,000 base pairs, which then you get this number, and RLD is just the radial loop domain, and then you do it again over 200 1,000 base pairs, and you get this, and that's where you find the translocation chromosome, which it's going to be between 785 and 6,280 radial loop domains. And that's question 3.
All right, sweet. I got 4 and 5, and I'm just gonna screen share real quick. Okay, and here in 4, we're talking about the lengths of this chromosome here. And if we see 4a says that the chromosome was stretched out linearly, how long would it be in micrometers? And we just take the number of base pairs and multiply it by the length of each base pair, and then we multiply that out to get to our micrometers instead of nanometers, and that gets us to nearly 1.5 third, if I'm right, micrometers. And if we move on to B, it says, what is the diameter of tuberculosis chromosome in micrometers? And you just do what you had in answer A divided by pi. It just takes the diameter times pi to make to get your circumference, and that's what we're doing here, is just dividing the circumference by pi to get the diameter, which comes to 477.3 micrometers. Then in part C, we have suppose the tuberculosis genome is organized into loop domains, with each loop domain containing 50,000 base pairs. If one of these loops was stretched out nearly linearly, how long would it be in micrometers? And so we just take that number of base pairs per loop, times it by the length, and then do the math to bring it out to micrometers. It comes to 17. And then part D, how many histones are found attached to the tuberculosis chromosome? We just take the number of base pairs it has in total and divide it by the number of base pairs that it's approximately in for the amount of histones, or amount of base pairs within a histone. And then it brings us to this range right here of nucleosomes. And then we multiply it by how many histones are in our nucleosomes, which is 8, and it comes to this range right here. Okay, and then part 5 has several different, and we're just trying to figure out what is what. And so the question is, which of the molecules in parts A and F are nucleosides? And when it comes to nucleosides, and I might need help remembering real quick from y'all.
Nucleosides were just attached to a sugar, right? It's just a base and a sugar.
I believe so.
And then nucleotides are the base pair, the sugar, and the phosphate group.
Okay, that makes sense.
Was it the single phosphate?
No, so it can have 1 to 3 phosphate groups.
That's right. Okay, so it was the sorry, I have a diagram here to help me out. Nitrogenous base with a ribose or a sugar, really, for the nucleoside, and then the nucleotides have the phosphates, either 1 or 3.
Mm-hmm.
And so that comes to AEF, and we need to, for the second degree carbon on the sugar, whether if it has an alcohol or not on that, to determine if it's a ribose or a deoxyribose. And it looks like the riboses are going to have an alcohol on that second degree, so you can see in F as well as E and in C for those. And then deoxyribose, of course, doesn't have that alcohol. You have the ABD. And then for the pyrimidines, those are the ones with the single rings. And that would be C, D, E, and F. And just scaling back up so everyone can see the video. And going back down.
Perfect.